Hi everybody, this is Dr. Hamid with your College Mathematics 120 class. Today we'll talk about section 5.5, which is about real numbers and their properties. Okay? So the objectives in this section are mainly about real numbers. Okay, so we'll start this lecture by defining a real number system. We will, talk about some subsets of the real number system. We will talk about some properties of real numbers. Okay, and then we'll apply these properties of real numbers to clock addition. Okay, we will introduce the term clock addition. I will explain more about that in a minute. So let's start with the set of real numbers. Okay, we talked about rationals and irrationals in the previous lectures. So the easiest way to look at it is this one: the union of rational numbers and the irrational numbers is called the set of real numbers. Okay, and now all other numbers that are contained in real numbers are called subsets of real numbers. Okay, what this means is this one: the real number system is a bigger one. Okay, real number system is the huge set like this one here. Okay, all the other sets are subsets of that. For example, the rationals and irrationals are contained in the real number system, so they are subsets of real number R. Okay, the natural numbers, okay, or the counting numbers, they are contained in the whole numbers because whole number is the bigger set because it includes 0. Okay, integers, they are bigger set than whole numbers because integers include negatives and positives, and all of these sets are included in rational numbers. Okay, now going back to the statement, all other number sets that are contained in real number set, which is this whole big circle, big oval shape thingy, are called subsets of real numbers. Okay, now let's look at a example of how to classify real numbers or classify numbers. Okay, bunch of numbers are given to you. Okay, different type of numbers. Let's classify them. It will sort of refresh our knowledge from what we learned from the previous sections, and it would explain things a little better. So let's look at what are the natural numbers in this set here. Okay, natural number is only natural number available here is this square root of 81. If you remember, the square root of 81 is 9. Okay, now we are talking about natural numbers. Natural numbers are counting numbers. Counting numbers are positive numbers which we use to count things. Okay, that is the only one in this given set is square root of 81, which is basically 9. Okay, 9 is the only natural number or counting number. If you look at other ones, there is something wrong with each one of them. -7 is negative number, it cannot be a counting number. This one is a fraction, cannot be. Okay, 0 is not included in natural or counting numbers. This one means 6 repeats, okay, itself, so it's a rational, it's not natural. Okay, this one is also irrational number, this one is irrational, this one is decimal, so everything is wrong with each one of them. The only qualifying natural number here is square root of 81, which is basically 9. Let's look at whole numbers. Okay, now if you pay attention to the previous slide, we talked about that natural numbers are the basic counting numbers, and whole numbers are if we add 0 to the counting number. So this one and square root of 81 is are our whole numbers in this system. Let's look at integers. Okay, now integers go one step further. So we want counting numbers. Okay, we want whole numbers, which including 0, and then we want negative whole numbers as well. Okay, so the negative whole number is this one, and these two we already talked about. So these three, 0, square root of 81, and -7 are our integers. Okay, now let's move on to a biggest, the bigger set, which is the rational numbers. Okay, if you recall, rational numbers are any numbers which we can write as a ratio of two integers. Okay, now the ratio can be in decimal, but the decimal has to uh, either repeat itself, like in this one here, square root 0.6. This line on it means it goes like 0.6666666, or it has to be a terminating decimal. For example, this 7.3. Okay, all these are rational numbers. The next obvious category is irrational numbers, and by irrational numbers we mean to look for those numbers, okay, whose decimal representation is non-terminating. They keep on going and going and going. Okay, so and they are square root of 5 and pi. Okay, and the last one is the real numbers. All of them discussed here are real numbers. Okay, so real number is a bigger set. Now to think about it, graphically, if we remember, we talked about a real number line which starts from minus infinity and goes all the way to infinity. Okay, anything which we can find on a real number line, on the number line, is called a real number. Okay, so they are all positive, negative, fractions, ratios, repeating decimal, terminating decimal, everything is on that is on the real number line is called real numbers. Now there are properties of real numbers. Okay, lot of properties actually. I will put all of them here, and then we'll explain more, a few in further detail. First of all, the main important property is called the closure property of addition. Okay, what does mean? Closure property means that if you take any two real numbers, add them up, the result will be another real number. Okay, so it's not if you add two real numbers and you get something else. So all real numbers are closed under addition. So the sum of any two real numbers is another real number. Okay, here's an example. If you have 4 square root of 2 is a real number, 5 square root of 2 is a second real number. If you add the two, the result will be another real number. So that's what means the thing is closed under addition. So real numbers are closed under addition. Similarly, and addition and multiplication are same things. Okay, so don't worry about that. Now we have the similar closure property for multiplication. Okay, which says the exact same thing. If we take two real numbers, multiply them, okay, then the result will be another real number again. Okay, if you take 10 and half, multiply them, then you will get another real number, which is 5 here. Okay, third property is the commutative property of addition. That means if you want to add 3 to 4, okay, or 4 to 3, doesn't matter, your end result will not change. Okay, if you are adding two numbers, real numbers, does not matter, the order does not change anything. Okay, so it does not matter if you put A first or B first. So for example, 13 plus 7 or 7 plus 13 will have the same answer. Okay, so sort of a common sense property here. Now then we have a similar commutative property for multiplication. If you want to multiply 4 times 2 or 2 times 4, does not matter. Okay, each will give you the same result. So this kind of property is called a commutative property of multiplication. Examples is here. If you multiply 7 times 13, that's 91, or 7 times 13 times 7, same thing. Okay, does not matter anything. Now these are the important ones. Few more. Okay, we can have 3 numbers. It's called associative property of addition. Okay, this property tells us the grouping does not matter. The grouping does not affect the end result. The way how you group, okay, you might want to group if you have 3 numbers A, B, C. Okay, it does not matter if you first find this sum or you first find this sum. Okay, A plus B plus C or A plus B plus C does not matter. Okay, so example is here. If you want to add, if you have 7 plus 2 plus 5 or 7 plus 2 plus 5, okay, so the end result will be same. So this is called associative property when you deal with 3 numbers or 3 things. Similarly, we can have associative property of multiplication. That also tells us the same thing. If you want to multiply 3 numbers, okay, does not matter which 2 you multiply first. Okay, now basic thing we know, if we want to multiply 3 things, we first have to multiply 2 of them. So it does not matter which 2 we choose. Okay, the end result will not change anything. Another important one is called distributive property of multiplication over addition. That means if you have a sum of 2 numbers and a third number is being multiplied, okay, so we can distribute it to each one of them individually. That means we can multiply A with B and A with C. For example, here it's explained, if you want to distribute 7 into 4 plus square root of 3, you can multiply 7 out. Okay, so it will be 28 plus 7 times square root of 3. Okay, and the interesting one is identity property. Identity is, as you might know, if it does not change anything. Okay, so if you the identity property of addition is you add something to a number and you get the same number. It does not affect it, does not change it. Okay, so now according to this property, 0 can be added to from a sum. You can add it either way. A plus 0 is a, or 0 plus a is a. Okay, so adding 0 does not change anything, so it's an identity property of addition. Last three properties are about multiplication here. Okay, so identity property of multiplication is, if you multiply anything with the 1, it remains the same, sort of, we know already. Okay, so if you multiply a with the 1 or 1 with a, it will still be the a. Okay, and the inverse property of addition is anything which you add to a given number and it produces 0. Okay, so this is called additive inverse as well. Okay, so this is called the additive property of addition. And the inverse property of multiplication is whatever number you are multiplying, if you multiply it with its reciprocal, okay, 1 over that, okay, and that produces 1, that will be a, that's called the inverse property of multiplication. The product of a non-zero real number and its multiplicative inverse gives 1. Okay, by multiplicative inverse means the reciprocal, 1 over that. Okay, so this gives us 1. If you multiply square root of 3 with 1 over square root of 3, that will produce 1 there. Similarly, 1 over 8 times 8 will give us 1. Okay, so you're multiplying the number itself with its reciprocal. Okay, in this example, I just cooked this example up so that you can understand what happened here. For example, I will give an example here, and your goal will be to identify which property has been used here. Okay, for example, in this one we have square root of 3 times 7 equals to 7 times square root of 3. Okay, you can see that this is commutative property of multiplication. Does not matter which number we write first when we multiply. Okay, so this is called commutative property of multiplication. Look at a second example. Here we have 4 plus 7 plus 6 and 4 plus equals to, in the parentheses, 7 plus 6. This is about grouping. Okay, grouping of 3 numbers. So this is associative property of addition. When we talk about 2, it's commutative. When we are talking about 3, it's associative. Okay, so in this one is associative property of addition, and it will not change anything. It will not change a thing if you how you group it. Third one is, suppose we have 2 and then parentheses 3 plus square root of 5, and then we distributed 2 here. So which property we used here? We used distributive property, okay, of multiplication over addition, going back to previous slides. As a last example, okay, this is about what produces 0. So we have 17 plus, and we add it into a minus 17, it produces 0. So it's additive inverse. Okay, so inverse property of addition, which takes us back to 0. Okay, so there are examples like this one in your homeworks. I want you to try those easy ones, but you have to be awake. You have to pay attention what's going on, which property you're using there. Now the second half of this lecture is is about clock arithmetics. Okay, now arithmetic is numbers. When we add numbers, we can add 1,000,000 to 1,000,000 and we will get 2,000,000. We can add 500 to 700, you will get 1,200. There is no limit, you just keep on moving. Okay, when we talk about clock arithmetic, we have a end number. For example, most of our clocks go from 1 to 12. Okay, or you might have seen some which go from 1 to 24. Okay, so all the 24 hours. So now in some situation we can also have a clock from 1 to 6. Okay, so by clock arithmetic we mean that we will go up until 12 and then we'll return back to 1 instead of keep going. Okay, suppose we want to add 2 plus 11. Okay, so it will be 13, but 13 is not here on the clock. Our result has to be present on the clock. Okay, so basically we are limiting limiting our numbers. Okay, so this is interesting. So just to develop a basic understanding, let me put some simple questions here. Suppose it is 8 o'clock right now. Now the question is, what will be time in 6 hours? So it's 8 o'clock right now. In 6 hours, what will be time? The answer is 2 o'clock. How do you know that? If you just add 8 to 6, okay, it will give us 14. But what I told you earlier is 14 is not acceptable number on the clock. Okay, our clock does not have 14. We are talking about 12, 12-hour clock here. Now, but we also know that when you reach 12, after that it is back, 12 is back to 0. So, therefore, since we are 14, so we need to do 2 more. So that's how our answer is 2 o'clock. Let's look at another one. Suppose it's 7 o'clock right now. Now the question is, what will be time in 14 hours? 9 o'clock. Again, how? You will add, in our clock arithmetic system, adding 12 will produce the same number. Okay, if you add 12, it will bring us back to the same time, since it's a 12-hour. Okay, so if it's 6 o'clock in the evening and 12 hours after that, it will be again 6 o'clock. Okay, so it will to the same time. Therefore, adding 14, it means you are adding 2 hours to the current time. Since it was 7 o'clock when we started, so now it will be 9. Okay, so you see how we have to remain on the clock. Even if we go beyond that, by simple addition, we have to come back to the clock logically, based upon the the clock we're dealing with. It's a 12-hour clock, 6-hour clock, or 24-hour clock, or any other clock. Okay, now the symbol we use for the clock addition is this addition and then this circle around it. Okay, so it's a special addition basically. So you think of this as a clock. Okay, suppose we live on a planet now, okay, where the day is 6 hours long. So this is our clock looks like. Okay, so according to this clock, our hours go from 1, 2, 3, 4, and then 6 means 0 here. Okay, the question is, if it is 2 o'clock right now, what will be time in 3 hours? Okay, so it's 2 o'clock right now. In 3 hours, just add 2 to 3 and the answer will be 5. Okay, so we'll simply add 2 to 3. The answer is 5. And we don't have to worry about anything. Why? Because 5 is still on the clock. Okay, so we just add the numbers and we remain inside the clock. So that's how you do the clock addition. 2 plus the special plus. Okay, 2 plus 3 equals to 5. This is called clock addition. Now things will get different if I had asked you to what will be time in 13 hours or 7 hours. Okay, then we'll go outside the clock and then we have to look at it logically. Let's look at another one. Okay, again we are on the same planet. Okay, say if it's 4 o'clock right now. Okay, what will be time in 5 hours? Now if you add 4 to 5, you will get 9. Okay, we will add 5 to 4, logically speaking, it will give us 9. Now using clock addition, we know that 6 is 0 right there, 7 will be 1, 8 will be 2, and 9 will be 3. So that's our answer. So 5 plus 4, which is in our daily language, 5 plus 4 is 9, but since 9 is not on the clock, we have to remain on the clock. It is 3 there. Okay, we are going in circles, and the key idea here is that 6 is 0 and 7 is 1 and 8 is 9, 8 is 2. Okay, like that. Okay, and the third example, again, I'm not gonna go over it. You can look at it again. Okay, now the idea here is we can use these examples, okay, to build a table, and this is called a 6-hour clock addition table. The idea is the same. If we have a 6-hour clock, as in our previous examples, I labeled them 0, 1, 2, 3, 4, 5, and 6 is 0. Okay, now what will be 7? 7 will be 1, 8, 9, 10, 11, 12, like this one here. Okay, now we normally don't write. Our clock only represents 0 to 1 to 0, 1 to 6. 6 is 0. Okay, we don't go beyond that, but in our head we know that the numbers keep on going and going and going, and similarly they will keep on going. If it is 12, then this will be 13, 14, 15, 16, 17, like that. Okay, now based upon that one, we can make a table, Okay, this is called a clock addition table. What it basically means is that, this is our addition, okay, and this row is the numbers on our clock. Okay, so we have 0, 1, 2, 3, 4, 5. They are the numbers on the clock. Okay, now if we have to add 0 to this any hour, okay, if we have to add 0 to 0, we will get 0. If we have to add 0 to 1, we'll get 1. 0 not going to change anything. It's that identity. If you have add 0 to 2, it will be 2. If you add 0 to 3, it will be 3. If you add 0 to 4, it will be 4. Okay, if you add 0 to 5, it will be 5. We remained in the clock. Okay, we did not go outside, so that's why it's called the identity. Okay, 0 is called the identity. Now let's look at 1 here. Suppose it's 0 clock right now, and what will be time after 1? We just add 1 to that, and that will be 1. If you add 1 to 1, that will be 2. Okay, if you add 1 to 2, it will be 3. If you add 1 to 3, it will be 4. If you add 1 to 4, it will be 5. Still okay. Now pay attention here. Okay, now if it is 5 o'clock right now, what will be time after 1 hour? We have to add 1 to 5, and that will give us 6. But 6 is not on our clock. 6 means 0, so it will be 0 here. Okay, our table will not go beyond 5. We will have 0 to 5, and that's it. Okay, similarly, if you add 2, everything will be fine, everything will be fine, everything will be fine unless you hit 6. When you add 2 to 4, you will go back to 0, and when you add 2 to 5, that means 7 is basically 1, so you go back there. Okay, now similarly, when you add 3, everything will be same for up until 5 here. When you add 3 to 3, that will give us 6. 6 is 0. That will be 1. That will be 2. Okay. Similarly, we can fill in the blanks in the whole table, and this is called a clock table. Okay, addition table for 6-hour clock. And let's say now I can ask you a question: can you build a clock addition table for 12 hours? Yes, you will go all the way to 12. They say 12 this way. But whenever your addition will give you 13, that will be 1. Whenever your addition will give you 14, that will be 2. Your table will have only entries from 1 to 12 in that case. Okay, not that complicated. It's just as long as your head is inside the clock, you're fine. Now the properties of the real numbers, still, even if we are restricting ourselves from 0 to 12, we're still in the real number system. Okay, so the properties of the real numbers apply to 6-hour clocks. So here we will look at some examples here. How can you tell that a set of 0, 1, 2, 3, 4, 5 is closed under the operation of clock addition? It is, because when we build a clock table here, okay, when we add these two numbers under clock addition, we still get the same number which is on the table here. Okay, so it's closed. The given set from 0 to 5 is closed under operation of addition, clock addition, because the entries in the body are the elements of the set. Okay, when we add two numbers on the clock, we get another number which is still on the clock. Okay, even though we get it after manipulation, but that's why we're using clock addition. We are not saying general addition. Okay, so the numbers on the clock are closed under the operations of clock addition. Okay, so similarly, let's verify the associative property. Okay, if it holds under clock addition or not. Suppose we want to add 2 plus 3. Remember that it's a clock addition this time. 2 plus 3 plus 4 equals to 2 plus 3 plus 4. Okay, so each side should give us the same answer. If you look at 2 plus 3, that's 5. Not a problem. 5 is on the clock here, so it will be 5. So we will have we will have 5, and then 5 plus 4, which is 9. What does 9 mean? 5 plus 4, that is 3 here on this side. Similarly, now this time let's add 3 plus 4, which is 7. Okay, so where is 7? 3 plus 4, 7 is just 1, and then plus 2 is 3. Okay, it means that no matter how we group it, as long as we follow the rules of the clock addition, these numbers are closed under associative property. Okay, Uh, as a last example, let's look at the identity. Okay, what is the identity item in the 6-hour clock? Now, identity element is which does not change anything. So, and that has to be 0. Okay, if we add 0 to 1, it is 0. 0 to 1 is 1. If you add 0 to 2, it's 2. 0 to 3 is 3. 0 to 4, it's 4. 0 to 5, it's 5. Does not change anything. Okay, so this is our 0. Okay, no, the identity is 0 here. Now let's look at the inverse one. Okay, according to the clock table, clock system, find the inverse of each element in the 6-hour clock system. We're talking about the inverse. When an element is added to its inverse, the result is an identity element. Okay, the question is, what produces the identity? Identity is 0. We already decided in the previous slide. Okay, so what are we looking for? What must be added to each element to get 0? Okay, element is given to you. Whatever we add, that will be our inverse. For example, if you add 0 to 0, okay, so that will produce 0. So the inverse of 0 is 0. Similarly, if you add 1 to 5, that what produces 0? So if you add 1 to 5, that will give us 0. So the inverse of 1 is 5. And similarly, the inverse of 5 is 1 as well. Okay. Similarly, if you add 2 to 4, that will produce 0. So inverse of 2 is 4 and inverse of 4 is 2. Okay. Similarly, if you add 3 to 3, that will give us 0. So the inverse of 3 is 3 basically. I hope you got the idea. As I said, it's not complicated. You have to make sure that you cannot, any number beyond that 6-hour clock system is not allowed. Thank you very much. I hope you enjoyed the lecture. Try the homework problems assigned. Do the quiz. Let me know if you have any questions. Thank you. Bye bye.